Every computer, from a calculator to a supercomputer, is doing exactly one thing, flipping millions of tiny switches, incredibly fast, in a pattern someone wrote down in advance. That's it. There's no deeper magic. Everything else, the operating system, the apps, the internet, is just layers of organization built on top of that one idea. This video builds that idea up from the very bottom. A single switch all the way to the machine you're watching this on right now. The switch at the bottom of everything is called a transistor. It lets current flow or blocks it based on a separate control signal. Wire a handful of transistors together in the right pattern, and you get a logic gate, a tiny circuit that outputs true or false based on its inputs. And OR and NOT gates are the entire alphabet. Every calculation a computer will ever do is built out of just these three. A transistor only really has two states, on or off. So computers represent everything, numbers, letters, images, as patterns of just two digits, 0 and 1. A single 0 or 1 is called a bit. String 8 of them together and you get a byte, enough combinations to represent a letter, a small number, or 1 pixel's shade of gray. There's nothing special about the number 2 here, except that it matches a transistor's two states perfectly. Binary isn't a choice, it's a consequence of the hardware. Logic gates don't just represent true and false. Wire them together correctly, and they can add numbers. A circuit called a half adder takes 2 bits and outputs their sum, plus a carry bit for when the result overflows. Chain several together, and you can add numbers of any size. This is the moment abstract logic becomes math. Every calculation your computer ever performs traces back to gates like this one. All that arithmetic happens inside one component, the CPU, and specifically a part of it called the ALU, the Arithmetic Logic Unit. Right next to the ALU, site registers, tiny, extremely fast storage slots that hold the exact numbers currently being worked on. Everything else in the computer exists to feed the ALU new numbers and store what it produces. A running program is really just a long list of tiny instructions, sitting in memory, waiting their turn. The CPU works through them one at a time, fetch the next instruction, decode what it means, execute it, then move to the next one. Billions of these fetch-execute cycles per second, one after another, is what makes a program feel instantaneous. A clock inside the CPU ticks at a fixed rate, and every tick pushes the fetch-execute cycle one step forward. That's what clock speed actually measures. Modern CPUs don't wait for one instruction to fully finish before starting the next. They overlap several at once, a trick called pipelining. It's the same idea as an assembly line. Even though one instruction still takes several steps, a new one can start every single tick. Registers are blazing fast, but there are only a handful of them. So computers back them up with a hierarchy of larger, slower memory. Cache sits just outside the CPU, small, fast, and holding whatever data was used most recently. Beyond that is RAM, much bigger, noticeably slower, holding everything a running program currently needs. RAM forgets everything the moment the power turns off. For anything that needs to survive a restart, computers use persistent storage. A hard drive stores data magnetically on a spinning disk, physically moving a RAID head to find it. That physical motion is what makes it comparatively slow. A solid-state drive stores the same data electronically, with no moving parts at all, which is why it's so much faster. Every one of those components, CPU, memory, storage, needs a coordinator. That's the operating system's job. It's the layer of software sitting between your applications and the raw hardware, deciding who gets to use what and when. Without it, every single app would need to know how to talk to your exact model of hard drive and exact model of CPU directly. A single CPU core can genuinely only do one thing at a time. So how does it feel like you're running 20 programs at once. The operating system rapidly switches between programs, running each one for a tiny slice of time before moving to the next. It happens so fast, thousands of times a second, that to a human, every program just looks like it's running simultaneously. Every running program acts like it has the entire computer's memory all to itself, with nobody else in the way. That's an illusion the operating system maintains called virtual memory. Each program gets its own private address space, invisibly mapped onto the real shared memory underneath. It's also what keeps one crashing program from corrupting another's memory. They're never actually touching the same physical space without permission. Nobody writes software in ones and zeros. They write it in a programming language, something built to be readable by humans. A compiler's job is translation. It reads that human-readable code and converts it into the exact binary instructions the CPU actually understands. Different languages sit at different distances from the hardware, but every single one, eventually, has to become the same raw binary before it can run. The CPU doesn't just compute, it has to talk to everything else too. Keyboards, screens, disks, and networks. That communication travels over buses, shared electrical pathways connecting components, carrying both data and instructions back and forth. Every keystroke, every pixel drawn to your screen is a message sent over one of these buses to or from the CPU. One computer talking to another breaks the message into small chunks called packets, each one labeled with where it's going. Those packets don't have to travel together or even take the same path. They just need to arrive and get reassembled correctly at the other end. That's the entire foundation of networking, a shared set of rules called protocols that every computer agrees to follow so the packets can be understood by anyone. The internet is really just an enormous network of networks, all speaking that same shared packet-based language. Every device on it has an address, a string of numbers, but humans don't type numbers. We type names, like a website's domain. The domain name system is a translator, a distributed directory that converts the name you typed into the actual numeric address your computer needs to send packets to. A CPU is built to do a few complex tasks one after another extremely well. A GPU takes the opposite approach. It has thousands of much simpler cores, all doing the same simple operation at once on different pieces of data. That's perfect for graphics, where the same lighting calculation needs to run on millions of pixels simultaneously, and it turns out to be just as perfect for training AI. Every idea in this video, transistors, binary, the fetch-execute cycle, still describes almost every computer in the world today. But the frontier is already shifting. Chips are approaching the physical limits of how small a transistor can get, which is why specialized hardware like GPUs and AI accelerators is taking over more of the work. Further out, entirely different physical approaches, like quantum computing, are trying to move past transistors altogether. Wherever computing goes next, it will still come back to this same question. How do you organize a switch, a signal, and a set of rules into something that can think? If this helped the whole machine click into place, go ahead and like the video, subscribe for more deep dives like this one, and let me know in the comments what you want unpacked next.